हेलो एवरीवन। आज हम बात करने वाले हैं ज्योमेट्रिकल आइसोमेरिज्म के बारे में। ज्योमेट्रिकल आइसोमेरिज्म मींस व्हाट आर द फैक्टर्स व्हिच आर रिस्पांसिबल फॉर ज्योमेट्रिकल आइसोमेरिज्म। In this lesson, we will be discussing the geometrical isomerism conditions, what are the requirements to show geometrical isomerism, and which type of compounds show geometrical isomerism. Geometrical isomerism means compounds having same molecular formula, same structural formula, but stereochemical formula is different, are called geometrical isomers. Now, structural formula means what? Same as structural formula. Structural formula means bond connectivity. The bond connectivity is same, but a stereochemical formula. Now, stereochemical formula means what? The arrangement of atoms, that is a three-dimensional arrangement of atoms in a space, is different. So, different 3D arrangement of atoms. Now, how the 3D arrangement of atoms or groups of atoms is different in a space? Let us take an example of alkene to understand how the stereochemical formula is different for alkene. So, for example, in case of butene, let us take example of butene. So, in butene, there is a carbon-carbon double bond between carbon 2 and carbon 3. So, this is the condensed structural formula for butene. Now, let us draw the complete structural formula for butene. So, in complete structural formula, let us start numbering from one end to the parent chain. And we know that there is a double bond between carbon 2 and carbon 3. So, first draw the double bond. Now, this double bonded carbon, methyl group is attached and one hydrogen atom. Similarly, other end also, one methyl group is attached and one hydrogen atom. Now we know that this carbon-carbon bond, so one bond is a sigma bond and second bond is a pi bond. Now how the pi bond formation takes place? We know that the pi bond formation takes place due to what? Due to lateral overlapping. Okay, so first draw the structure of this pi bond overlapping. Now this is carbon-carbon single bond. Now this methyl group, so we have methyl group which is below the plane and one hydrogen atom above the plane. Similarly, one more methyl we have which is below the plane and one hydrogen atom above the plane. Now overlapping of these p orbitals. So we have two p orbitals and these p orbitals are parallel to each other and each p orbital contains one electron. Now when these orbital overlaps results in the formation of pi bond. And for effective overlapping of these orbitals, what is the requirement? So orbitals should be parallel to each other. Then only there is a formation of pi bond takes place, effective pi bond formation takes place. So these half-filled orbital with opposite spin overlaps and there is a formation of pi bond. Pi bond formation takes place because these loops overlaps and we get a pi bond, right? Now, so if we rotate this carbon-carbon double bond, then what will happen? Let us fix one carbon atom by keeping one carbon atom fixed. So I'm keeping this one carbon atom fixed and I'm rotating the second carbon atom. So these are the orbitals arrangement, first orbital, p orbital. Now what I'm doing, I'm rotating the second carbon by keeping the first carbon fixed. So let us rotate the second carbon. So by rotating, what will happen? The methyl group methyl group is present below the plane. Okay, now what will happen? It will come down and hydrogen goes up. This hydrogen will goes up. So we'll get this type of arrangement. Hydrogen goes up, methyl come down, and we have one orbital. The orbital also goes out of plane because of rotation. So we are rotating this almost 90-degree rotation about the carbon-carbon bond. So what will happen now? This orbital goes out of plane. So because of this, these orbitals are not parallel to each other, right? Not parallel. So there is no overlapping, means no overlapping. It means now when we rotate the carbon-carbon double bond, what will happen? The bond break, pi bond break, and pi bond break, right? So this rotation around the carbon-carbon bond is a restricted head. We cannot rotate it without breaking the bond. So around this system, around this carbon-carbon double bond, the two isomers are possible because of this restricted rotation. Now, I'm drawing the structures, what kind of different formulas are possible because of this restricted rotation for same compound. I'm taking again the same compound. Now, how the different compounds are possible. So, this is one compound we have for but2ene, where methyl groups located on same site of double bond, and one more compound we have where methyl groups are located exactly opposite side of a double bond, right? Now, in the first compound, if we look at the arrangement of the atom, then we'll get to know that methyl groups are lies on the same side of double bond. But if we take the second compound, in second compound, the methyl groups are located exactly opposite side of a double bond, right? So in first compound is known as what? Cis form, where two groups lies on same side, and the second compound is known as a transform, where two methyl groups are located exactly opposite side of a double bond. So it is known as a trans. So these are the two different compounds. And these two different compounds are possible because of their what? Because of their the arrangement of the atoms in a space. So because of their different arrangement of atoms in a space. So these two compounds have different physical properties, right? So they have different physical properties. Now, next point is now let us discuss first what are the different conditions which are responsible for to show this type of isomers, and these isomers arises because of restricted rotation. So this rotation around this double bond is restricted. Similarly, around this double bond, the rotation is restricted, so we cannot rotate it without breaking. If we rotate, what will happen? It will dissociate. But without dissociation, it is impossible to rotate the carbon-carbon double bond by keeping one carbon atom fixed, right? Yes. Now, अब हम डिस्कस करते हैं what are the different cases जहाँ पे geometrical isomerism होता है. तो first हम बात करेंगे double bonded system के round, right? Yes. So now first the restricted rotation around carbon-carbon double bond or carbon-oxygen double bond, nitrogen-nitrogen double bond, or carbon-nitrogen double bond, etc. This type of system. Now, let us take one system first, system that is a carbon-carbon double bond. Now, if you take the carbon-carbon double bond, right? So rotation is restricted. Now, what is the requirement? The first requirement is there should be restricted rotation must be present. So yes, this type of system, there is a restricted rotation around the carbon-carbon double bond. But such type of rotation is restricted rotation is not there in case of carbon-carbon single bond, or carbon-carbon triple bond. We can rotate because it is a linear molecule, right? Yes. So if we take the carbon-carbon double bond, and if the groups attached to the double bonded systems are suppose A and B, this type of system, it will works. It shows a cis-trans isomer, it shows a geometrical isomers. Or if we take the system like carbon-carbon double bond, and the groups like AB and AD groups are attached, then also geometrical isomer is possible. So what is the requirement? The different groups should be bonded to the carbon-carbon double bond. So here, this is system. The restricted rotation is there around the carbon-carbon double bond. We have this system, and here different groups are attached. One A atom and B atom. These are two different atoms. They are bonded to the carbon-carbon double bond. Similarly, here also we have two different atoms A and B, which are bonded to the carbon-carbon double bond, right? So system is a planar because of what? Because of the sp2 hybridization, sp2 hybridization of a carbon atom, right? System is planar due to sp2 hybridization of a carbon atom. Now in second system also, we have a geometrical isomer A, B, two different groups are bonded to carbon-carbon double bond. And here also A and D, two different groups are bonded to the carbon-carbon double bond. So here also geometrical isomer is possible. Now one more possibility is if the all groups are different. For example, A, B, and D and E. If all groups which are bonded to the double bonded system are different, then also geometrical isomer is possible. So these are the requirements. So this is second condition. So first condition, what is the first condition? There should be restricted rotation. And second condition is different groups should be bonded to the double bonded system. And third condition is what? Third condition is the groups which are responsible to show geometrical isomers should be lies in same plane, right? So three conditions you have to remember. Now, in case of this carbon-oxygen double bond, how geometrical isomer takes place? Suppose if you take the system like carbon-oxygen double bond and groups A, B groups are bonded, suppose to the carbon. We know that there are two lone pairs on oxygen, right? Now here the lone pairs, two lone pairs are identical, right? So this is same, two lone pairs are same. So in such a case, is no geometrical isomer, right? But if we take the system like a carbon double bond oxygen, A, B groups are bonded to carbon, and there is one lone pair on oxygen and one hydrogen, this type of system. Now we have different groups, one lone pair is there, hydrogen, which are bonded to oxygen, right? And A, B groups are bonded to carbon. So we have totally different system. So here geometrical isomers are possible, okay? Now in case of carbon, nitrogen, how geometrical isomer takes place? So if we take a nitrogen system, now nitrogen, there's a lone pair on nitrogen, and if the different groups are attached, for example, hydrogen, so here one lone pair and one lone pair is there, and one hydrogen is there, different system. So here also geometrical isomer is possible. So if you replace this hydrogen atom by using methyl group, then also geometrical isomer is possible. If we keep one hydrogen atom and one methyl or one phenyl group, then also geometrical isomer is possible, this type of system, right? Next is around carbon double bond nitrogen type of system. Here carbon R dash attached, and there's one lone pair on nitrogen and OH group, right? So C double bond N type of system. So these are the possible cases where geometrical isomers is observed. So first conditions I'm writing. What is the first condition? So we have to remember the three conditions which are necessary to show geometrical isomers. So first conditions to show geometrical isomers. So first condition. What is the first condition? So first condition is restricted rotation. Restricted rotation is an essential condition to show this geometrical isomers. Second condition, different groups should be bonded to carbon-carbon double bond, or carbon-oxygen double bond, carbon-nitrogen double bond, or nitrogen-nitrogen double bond. And third case is groups which are responsible to show geometrical isomers should be lies in same plane. So three cases you have to remember, right? Third also I'm writing. Groups which are responsible for geometrical isomers should be lies in same plane. Now, if the hybridization is sp2, then groups are nearly lies in same plane. So we have to check the hybridization of the carbon-carbon bond or carbon-nitrogen bond or carbon-oxygen bond. Methyl carbon-carbon hydrogen, one ethyl group and one more ethyl group. This type of compound. Now in this compound, the restricted rotation is there. Around carbon-carbon double bond, there is a restricted rotation. The first condition, this compound is satisfying the first condition. But what about the second condition? Now check the second condition. The ethyl group is there and one more ethyl group. So two identical groups, right? Two same groups are bonded to the carbon-carbon double bonded system. So in such a cases, there is no geometrical isomer. So for this compound, geometrical isomer is not possible, right? Now, next case is, suppose if we take the example, carbon, carbon, and here suppose one propyl group is there, one OH group is attached, one SH, and one hydrogen, this type of system. Now, around a carbon-carbon double bond, first condition is there is a restricted rotation is there around carbon-carbon double bond. Now, check the groups. The groups, so 4 different groups are bonded. So, yes, and hybridization of the carbon-carbon system is sp2, right? So, it means this planar system. So, all 3 conditions, this compound is satisfying. It means the geometrical isomers are possible, right? Yes. Next is, suppose if the compound is given, compound containing carbon double bond nitrogen, one ethyl group is attached, one methyl, there's one lone pair on nitrogen and one OH, right? So this system, carbon double bond nitrogen, yes, we have restricted rotation around double bond. Then 4 different groups are attached, methyl, methyl, one lone pair is also there, and OH group, right? So 4 different groups, and all these groups are nearly lies in same plane. So this compound is satisfying all these conditions. It means it shows geometrical isomers. Now the carbon double bond nitrogen containing compounds, and if the OH is bonded to this system, this type of compounds are known as what? Ketoxam. So this is general formula for ketoxam, R dash double bond and OH. General formula for ketoxam, and in case of aldoxam, general formula is RCH double bond and OH. So this is general formula aldoxams. So both these compounds, ketoxam as well as aldoxams, both these compounds shows geometrical isomers. Okay. Now next system is around the nitrogen double bond. In nitrogen double bond, we know that this group is known as what? This group is known as the azo group. Let us take one lone pair, place one lone pair on nitrogen. This type of system, this is an azo compound we have. Now these R and R dash may be same or different. So first condition is there is a restricted rotation. Second condition we have to check is the different groups are bonded to nitrogen, double bonded nitrogen or not. And third condition, nearly planar system. So yes, one lone pair is attached, one R dash group, and to the another nitrogen, one lone pair and R group. So 4 different groups are attached. So we have this planar system also, right? So this compound, azo compound, also shows geometrical isomers. So these are the possible cases. If the compound contains multiple bonds, then how to identify that compound show geometrical isomers or not? Multiple bonded compounds, okay. In case of alene system, in case of Allen's system, Allen means what? Allen system means there is a continuous double bonded system. Continuous double bonded system, this type of system. Now let us check in this Allen system, the geometrical isomer is possible or not. Now in such a cases, first draw the 3-dimensional arrangement of the particles and check the conditions. The given compound is satisfying all the conditions or not. Okay, so I'm drawing the 3-dimensional arrangement of these particles. So this compound can be written as ACB, where A and B lies in a plane. We have one pi bond, one more pi bond, p orbitals, And at the terminal end, we have one A atom which is present below the plane and one A atom above the plane, this type of system. So in this case, because of the number of double bond is equal to 2. Number of double bonds is equal to 2, which is even number, right? So in case of even number system, continuous double bond, the atoms which are directly bonded to terminal carbon do not lies in a same plane. Okay, so this is not a planar system. So this is non-planar system, right? And we know that it's non-planar system do not show geometrical isomer. So here groups bonded to terminal carbon are different, but the system is non-planar. So non-planar do not show geometrical isomer. Geometrical isomers are not possible. So we have to remember, if the alene system contain even number of double bond means the system is non-planar and the geometrical isomers not possible at all, right? But if we take the system containing odd number of double bond, for example, let us take a system containing 3 continuous double bond. Now here what will happen, here we'll get the molecule is planar. Let us draw the structure, three-dimensional structure for this. So we have A and B atom which are lies in same plane. First I'm drawing all this carbon connectivity, right? Now draw this pi bond system we have, right? And then this type of overlapping we have. Now at the end, what will be the arrangement of the atoms? So the arrangement of atoms is A, B. So we'll get this type of arrangement. And now if the number of pi bonds is odd number, it means that system is planar. Okay, so here this is a planar molecule, and planar molecule we have to check on 3 conditions to show geometrical isomers. First, we have to check is there restricted rotation? So yes, yes, there is a restricted rotation around the double bond. Second condition we have to check is the groups bonded to terminal carbons are same or different. So in this case, the groups are different, right? AB and another terminal also AB, the groups are different. And third condition, the atoms lies in same plane, it's a planar system. So this compound is satisfying all these 3 conditions of geometrical isomers. So yes, this compound shows geometrical isomers, right? Yes. Now, next is, so in short, you have to remember, if the number of double bonds even, then no geometrical isomer. No geometrical isomer. And if the number of double bond is odd, then check conditions. Check conditions of geometrical isomers. If compound is satisfying the all 2 conditions of geometrical isomers, it means that compound shows geometrical isomers. Now, next case we'll discuss is in case of cycloalkanes. Cycloalkanes. What are the requirements? Which type of cycloalkanes can show geometrical isomers? So one point you have to remember here, in cycloalkane, in substituted cycloalkane, compound containing at least 2 sp3 carbon having different groups shows geometrical isomers. So this condition we have to remember for substituted cycloalkanes. So if any substituted cycloalkenes, we are talking about, not alkenes. If the substituted cycloalkene is given, then we have to remember one point, that is, if the compound contain at least two sp3 carbon having different groups, then only geometrical isomer is possible. For example, in case of 1,2-dimethyl cyclobutane. Now check, this compound shows geometrical isomer or isomers only, right? So this carbon is sp3, similarly second carbon is also sp3, so we have two sp3 carbon, and check the groups are different or not. So one methyl group is there, one hydrogen is also attached to this sp3 carbon, and then different system we have, right? So four groups are different, similarly around this carbon also, four different groups are present, right? So two carbons are there. Now, how these compounds show geometrical isomer? So yes, this compound show geometrical isomer. Now, what are the structures of this compound? In this case, this 2-methyl group, we can place this 2-methyl group above the plane, or 1-methyl group above the plane and 1-methyl group below the plane. Okay, two examples are possible for this system. 1,2-dimethyl cyclobutane. So first compound where two methyl groups lies above the plane is known as what? It is known as a cis. And in second compound, one methyl group above the plane and second methyl group is below the plane. Such a type of system is known as what? Trans system, right? So we have cis and trans system for 1,2-dimethyl cyclobutane, right? Yes. Now second example. Second example is, now cyclopentane. Suppose if the compound is given, so now in this given compound, we have to check two sp3 carbons are there with different groups or not. So now check here, one methyl groups are there, and these methyl groups are same, right? Methyl groups are same. So at this carbon, no geometrical isomer. Now check next carbon. In next carbon, one this bromine is attached to this carbon, one hydrogen, and two different groups. Similarly, this sp3 carbon also, four groups are different. So around this two sp3 carbon, the geometrical isomers are possible. Cis and trans isomers are possible for this compound, right? Yes. Next is so next example, in this system also, 1,2-dimethyl cyclohexane, around this carbon atom, sp3 hybridized carbon atom, two groups are different, so geometrical isomer is possible, correct? So if any two different groups are, any two sp3 carbons are there in the cycloalkane, then geometrical isomers takes place, right? Yes. Now, one more system we are going to discuss now. The third type is the cycloalkenes. Geometrical isomers in cycloalkenes. Cycloalkenes. Cycloalkene type of compounds, cyclopropane, cyclobutene, cyclopentane, cyclohexane, and cycloheptene. Now, these compounds in cycloalkenes, up to 7-membered ring, they do not show geometrical isomer, because these compounds, they exist in cis form only. They do not exist in trans form. So this form, this ring is a cis form. Here, this similar type of group lies on same site, and hydrogen lies on same site. So these are the cis form. If we take any compound, we'll find hydrogen lies on same site. So these forms are what? Cis form, right? And these compounds, up to 7-membered ring cycloalkenes, they do not show geometrical isomers around a carbon-carbon double bond, because they exist only in cis form. So, but if we take the 8-member ring or 9-member ring, 10-member ring, 8-member ring onwards, they show the geometrical isomer, including 8-member ring. they show geometrical isomers. For example, if we take, for example, suppose the compound is, let us count the number of carbon atom. So in this compound, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 carbon atoms, right? So 10 member ring. Now, one double bond is there. Now, in this double bond, let us identify this form. So we have one hydrogen atom now lies on same side. So this form is a cis, right? But in a trans form, arrangement of the groups is, so this is double bond we have. Now this system where hydrogen lies exactly opposite side. So this system is known as what? Trans, where hydrogen are present exactly opposite of a double bond, right? So this is a trans form. Okay. So in cycloalkenes, what you have to remember, till 7 membered ring, they do not show geometrical isomers. But if the number of carbon atoms is equal to 8 or more than 8, then yes, in cycloalkene, geometrical isomer is possible. So if the alkene is given, then we'll check 3 conditions. If it is satisfying all 3 conditions, it means yes, it shows geometrical isomer, right? Yes. So butene is given. We know that in butene, this is the structure of butene. First, draw the structure butene. Now, first condition in alkene, you have to check is there restricted rotation or not. So yes, there is a restricted rotation around carbon-carbon double bond. Second condition we have to check is different groups are bonded or not. Methyl and hydrogen, different, right? Methyl and hydrogen. So we have different groups. Methyl and hydrogens are different. Similarly, in second carbon also, one hydrogen we have and one methyl group. So atoms are different. So, and hybridization of the carbon, double bond carbon sp2. So system is planar. So yes, the butene, it shows geometrical isomers. Similarly, pentene. In pentene, first draw the structure. Pentene. So there is a double bond at carbon between carbon 2 and carbon 3, right? Yes. So this is the structure of pentene. Now in pentene, check the groups are same or different. So around this system, around the carbon-carbon double bond, around this system, check the groups are same or different. So one hydrogen is attached and methyl group, carbon, hydrogen, and one ethyl group is attached. So yes, all groups are different. So this compound also shows geometrical isomers. Now third compound, in third compound, around this system, carbon-carbon double bond, groups are different, right? Groups one hydrogen. So we have to write a complete structural formula to understand it. So I'm writing complete structural formula: C2H5 CH double bond CH CH2I, right? So around this system, 4 groups are different. So yes, this compound also shows geometrical isomer. In next example, here 2 ethyl groups, 2 identical groups are attached. So these groups are same. Same groups are directly bonded to carbon-carbon double bond. So there is no geometrical isomer around carbon-carbon double bond. Only single double bond is there. So no geometrical isomers around the carbon-carbon double bonds because groups bonded to one of the carbon atoms are identical, right? Yes. Next is example number 5. Now, in example number 5, A2 groups are attached, means AA are identical. This is actual complete formula, complete structural formula for given compound. So here AA groups are same groups. Similarly, BB groups are also same, identical groups are attached to the carbon-carbon double bond, right? So if the groups are identical, it means no geometrical isomer. In second compound also, in second compound B2, that is identical groups are bonded, so no geometrical isomer. But in next example, where different groups are bonded to the carbon-carbon system, right? So here different groups are bonded. So yes, geometrical isomers are different. So we have to check the atoms bonded to carbon-carbon double bonds are same or different. So A and B are totally different, right? So different A and B. And in this compound, A lies on same side, so this form is a cis form also, cis form. So in trans form, A and B lies on opposite side, identical groups, right? Yes. Now in example number 8, so the formula is, this is known as what? This is known as a condensed formula. If any condensed formula is given, then first we have to expand it. We have to write a complete structural formula for that compound. Then only it is possible to identify. So first, identify the bond connectivity. In the compound, the carbon bond is given. Because this is carbon-carbon bond. So I'm writing first the carbon-carbon bond. I don't know the single bond is there or double bond. So first I'm writing the single bond. I'm checking the valency of the carbon when chlorine is attached, bromine. Similarly to the another carbon when chlorine and bromine is attached. Now valency of the carbon is 4. So we have to add one more. We have to add one pi bond, right? Yes. Now in this system, the groups are different. Different groups are bonded, right, to the carbon-carbon double bond. So yes, this compound also shows geometrical isomer. Next example. In next example, here also the condensed form is given. Carbon condensed form. You have to expand this for we have to write a complete structure formula for this condensed form. So carbon-carbon, I'm writing first single carbon-carbon bond, then one hydrogen is there, deuterium, and to the another terminal, one chlorine as bromine are attached. And the valency here, 3 bonds are there. We have to make it 4. Let us add one pi bond to the across carbon-carbon bond, right? Between carbon-carbon. So yes, this compound also shows geometrical isomers because different groups are attached. Now next example, carbon-carbon, bromine, chlorine, and the one terminal, another terminal, CH3 groups. Now here CH3 groups are identical, so no geometrical isomer. Groups are identical, geometrical isomer not possible. Next example, first carbon-carbon I'm writing single bond, then chlorine-bromine bonded to terminal carbon, and another terminal carbon, one methyl group we have, one NH2 group. Now check the groups are same or different. All 4 groups are different. Yes, geometrical isomer is possible, right? Next, 2,3-dimethyl butane. So we have butane. This is butane and 2,3-dimethyl. So in butane, alkene part, there is no restricted rotation. No geometrical isomer is possible for alkenes part, right? Yes. Next is question number 13. In 13, 2,3-dimethyl butane. So we have butane and 2,3-dimethyl. Now in 2,3-dimethyl butane, these groups are identical, same group, no geometrical isomer, no geometrical isomer. Next is pentane is given. So we have pentane. And it is 2-methyl pentane. So in pentane, alkanes part, no geometrical isomer. There is no restricted rotation. Next is butadiene is given. And one phenyl. So at carbon number 1, there is a phenyl. Butadiene. 1,3-butadiene, right? Yes. CS double bond CS. So now in this system, 1,3-butadiene, and there is a phenyl group at a carbon 1. In this system, 2 double bonds are there. So we have to check each individual double bond. Now around this terminal double bond, there is no geometrical isomer because groups are same identical hydrogen are attached to the carbon-carbon double bond. Now check second carbon. In second carbon, one hydrogen we have. So in second carbon, one hydrogen, one phenyl, one hydrogen, one different bulky system is there. So in second carbon, all 4 groups are different. So yes, geometrical isomer takes place. So in this compound, around 1 double bond geometrical isomer takes place, but around second double bond, there is no geometrical isomer. So overall molecule shows geometrical isomer, right? Yes, overall molecule shows. Next is 1,3-butadiene. So in 1,3-butadiene, terminal hydrogens are same, no geometrical double bond around carbon-carbon. Similarly, we have to check another carbon-carbon bond. Here also terminal groups are same, no geometrical isomers. So 1,3-butadiene, it do not show geometrical isomers, right? Yes. Next example. 2-methyl pentene. So this is pentene we have and a 2-methyl group, right? So here two hydrogen atoms are identical, same hydrogen atom. So no geometrical isomers. Malic acid. In malic acid, this is uh, existence cis form. This is cis form actually. Malic acid. So yes, malic acid shows geometrical isomers because the different groups are attached. So this is a cis form and cis compound. In fumaric acid, this is a trans form. It exists in trans form. Two carboxylic acid groups are there. Two carboxylic acid and two hydrogen atoms. Two hydrogen lies on opposite side, so it is trans. And when two hydrogen lies on same side, it's known as a cis form, right? Yes. Next example may two chlorine groups are given, which are directly bonded to carbon atom. Similarly, two bromine atoms are also. So groups are identical, no geometrical isomers. If the groups bonded to carbon are identical, the geometrical isomer is not possible, right? Yes. Next is 1,2-dimethyl cyclohexane. Now cyclic system is given 1,2-dimethyl cyclohexane. So in cyclic system, we have to check one condition, that is at least two sp3 carbon containing different groups. If two sp3 carbon atoms are there containing different groups, it means that compound show geometrical isomer, right? So this carbon is sp3, second carbon is also sp3, two different carbon atoms. So yes, geometrical isomer is possible. Next example may also two different carbon we have. So how this example shows geometrical isomer? So in two isomers are possible. Both chlorine above the plane and hydrogen below the plane. And in second case, one chlorine above the plane, one hydrogen below the plane, and one hydrogen above the plane, one chlorine below the plane. So this first form is known as what? Cis form, and second one is known as trans form. So we need two sp3 carbon. I need to at least two sp3 carbon with a different group show geometrical isomers. In 23rd, example number 23rd, may check the carbon. Here sp3 carbon, sp3 carbon, and sp3 carbon. So three sp3 carbon atoms are there. So yes, 23rd example also show geometrical isomers. Next 24th. In 24th, may around carbon-carbon double bond, no geometrical isomers, because we know that in cyclic system, till 7 metering, cycloalkenes do not show geometrical isomers. But if the so we have to check another condition, that is sp3 carbon. So one sp3, two sp3. So two sp3 carbon. So around this system, yes, this compound shows geometrical isomers. Two chlorine above the plane. Both chlorine above the plane is known as a cis, right? And hydrogen below the plane. And in second case, one chlorine above the plane, hydrogen, and one hydrogen above the plane, one chlorine below the plane. That is trans, right? Yes. Next example. Next example may no sp3 carbon around carbon-carbon double bond, no geometrical isomer because 6-member ring. 26 also carbon-carbon double bond, no geometrical isomer. Only one sp3 carbon atom is there. One more sp3 is required, no geometrical isomer. Next example may around carbon-carbon double bond check. The groups hydrogens are same groups are attached, no geometrical isomers around carbon-carbon double bond. Next example, same hydrogen is attached, no geometrical isomer is possible, right? Yes. Next is so we have to check around the carbon-carbon double bond. Now check CH-Cl. So here groups are different, but another side CH2 we have CH2 again CH. Here also CH2 CH. So these groups are identical. So this is identical system we have. So no geometrical isomer around carbon-carbon double bond. In next compound, compound is given. One methyl group is bonded to this cyclohexane part, CH-Cl. Now around the CSCl groups are different. On hydrogen we have chlorine groups are different, and here also we have different groups, right? So geometrical isomer possible. Next is around carbon-carbon double bond, no geometrical isomer. Carbon-carbon double bond, no geometrical isomer, right? In 32, example 32, we have to check at least two sp3 carbon containing different groups. So this carbon is sp3, we have two sp3 carbon. So yes, geometrical isomer is possible. So at least two sp3 carbon, at least two, we have these two sp3 carbon, OH group is attached and hydrogen, right? Yes, so geometrical isomer is possible. Next is next example में CH2 groups identical and other side of carbon also CH2 same, no geometrical isomer. Next example CH2 same, no geometrical isomer. In 35 में geometrical isomer is possible because here the groups are different, and we check this type CH2 and we have this CH2 groups are totally different. So yeah, geometrical isomer is possible. Then 36th में CH methyl groups are different, one hydrogen methyl. But if we take another side of the carbon-carbon double bond, same groups are there, same groups. So no geometrical isomer around the carbon-carbon double bond, right? Yes. Now, next example में carbon-carbon double bond, no geometrical isomers because hydrogen atoms are same. So overall molecule, it do not show geometrical isomers. 38, around carbon-carbon double bond, no geometrical isomers, but we have two sp3 carbon atoms. So around this sp3 carbon atom system, geometrical isomer is possible. 39, methyl groups are same. So around carbon-carbon double bond, no geometrical isomer. Next example, double bond in cyclic system, till 7-membered ring, there is no geometrical isomer, around double bond, but two sp3 carbon atoms we have. So yes, geometrical isomer possible around these two sp3 carbon atoms. Around double bond, no geometrical isomer because same groups are bonded, but two sp3 carbon atom we have, two sp3 carbon. So yes, around this system, geometrical isomer takes place. Overall molecule show geometrical isomers. Around carbon-carbon double bond, chlorine and hydrogen groups are totally different. Yes, and here also we have one system, chlorine is attached, different groups are bonded. So example shows geometrical isomers possible. In next example, hydrogen, same groups are given, no geometrical isomers because groups are same. So around carbon-carbon double bond, but two sp3 carbon atoms are there, two sp3 carbon. So around this system, geometrical isomer takes place. Overall molecule show geometrical isomers. Next example में two methyl groups are there, sp3 carbon, different groups are attached. So yes, molecule show geometrical isomers, right? Yes. Next, few cases of alene system. In alene system, we know that for the planarity, for the planar structure of the molecule, how many carbon-carbon double bonds are needed? Even number or odd number? We know that even odd number of carbon-carbon double bonds are required, right? Then only the system is planar. In case of even number of double bonds, system is non-planar. So now first we have to check how many carbon-carbon double bonds are there. So this total 3. 3 means odd number, right? So it means system is planar. So in planar system, now we have to check second condition. The groups bonded to terminal carbon atoms are same or different. So here methyl groups are given same. So around this system, we check this system, then there is no geometrical isomers around this system, right? But if we take this cyclic ring part, in cyclic ring 2 sp3 carbon, so yes, around this system, geometrical isomer is possible. Overall molecule show geometrical isomers because of these two sp3 carbon. So if any cyclic system is given, then we have to check sp3 carbon also, right? Yes. So overall molecule show geometrical isomers. not around the alene system, but because of this cyclic ring part. Yes, next example is, so next example we have two sp3 carbon atoms. So this compound also can be written as phenyl groups bonded to cyclohexane at 1/4 position. So yes, two sp3 carbon we have two different groups. Geometrical isomer is possible. In 47 also similar type to sp3 carbon geometrical isomer possible. Okay, 48. In 48 may I'm drawing the structure lone pair also. Lone pair OH group, double bond, and one ring is given, again double bond, nitrogen, one lone pair, and OH group, like this. Now, in this case, this double bond, again ring, double bond. So system is planar, right? Double bond, ring, and again double bond. So we have to, so total double bond plus ring, the number is odd, 3, right? So it is odd number, it means system is planar. Now this form is known as what? Cis form, where lone pair lies on same side. Lone pair lies on same side is known as a cis isomer, and if the lone pair lies on opposite side, then known as a trans, right? Yes. Next, 49. In 49 may methyl groups are identical. The system contain odd number of double bond, odd number, but that is, yeah, it is planar. But these groups are same, so no geometrical isomer, not possible. In next example, we have odd number of system again. That's lone pair on nitrogen, hydrogen, lone pair on nitrogen, hydrogen, right? Yes. So here, lone pair on one lone pair we have on hydrogen, lone pair hydrogen. Different groups are attached. Geometrical isomer is possible. Compound is planar, right? Yes. So this is all about the today's the geometrical isomer.